Okay, so today we're going to talk a little bit about entering expressions into your calculator. Then we'll spend the rest of the evening on polynomials. So let's get started. Key ideas that essentially on the mathematical reasoning test, you will be using a scientific calculator, as you already know, and you want to make sure that you're following the order of operations, as I mentioned in the last class as well. Use the change key sign to enter negative numbers. Use the grouping symbol keys to change the order of operations. So when you take the test, you may either use your handheld or the online version of the TI-30 XS Multiview, and you'll be given this to use on the second part. This calculator, like most scientific calculators, uses algebraic logic, which means that it follows the order of operations that we discussed last class. So it sounds like you'll only be allowed to use your calculator on the second part of the test. You need to practice using a scientific calculator with algebraic logic. You can find out whether your calculator uses algebraic logic by running the simple test. You can just try pressing 4 times 3 and then x squared button and then press enter. Or your calculator may have an equal sign. Mine has both an enter and an equal sign. If the display reads 36, then your calculator uses algebraic logic. And if it reads 144, it's not using algebraic logic. So you should find another calculator to use. So this is just something for you to test what kind of logic your calculator is using. In this example, we're told to find the value of the expression 2x squared plus 3x minus 5 when x equals, and this should read, I just wanted to show this slide because the mistake, I got a lot of mistakes in the book in this particular section of the chapter. So just, I guess, pay attention to this, maybe use the slides to correct the mistakes in your book so that you don't get confused when you're studying on your own. Just know that this is a mistake. It should read x equals -4, but it reads x equals x4. So just have that in your mind that that's a mistake. So I corrected it anyway on this next slide. So when you come to the x variable, just enter -4 by pressing the negative sign or the change key sign, and then follow with the remaining order, same way that the expression is written out in the question. So enter the expression exactly as it appears. You should get a value showing 15 as the right answer. Okay, so just practice using your calculator to get that expression in there and make sure that you get the right answer. To check your work when you're using a calculator, you want to enter each calculation twice. And if the results are the same, then you know that you probably pressed the keys that you intended on. Expressions are sometimes contained using grouping symbols to show a different order of operations. So you can enter grouping symbols in the scientific calculator. And on the TI-30 XS Multiview, the grouping symbols, open and close parentheses, are found right above the 8 and 9 digits. When you enter the left or the open parentheses symbol, the calculator waits for you to enter the right or the closing parentheses before it calculates what's inside the parentheses. So just make sure that you've correctly entered everything that needs to go in there. Then be sure to close your parentheses before you ask the calculator to return an answer, or essentially before you press enter. In this particular example, we're told to find the value of the expression 2, open parentheses, x plus 4, close parentheses, plus 5x over 3. When x equals 4. And as we've discussed last time, since we're given the value of x, all you need to do is go back to your expression, enter 4 everywhere where you see x. And I'm just noticing this is reading x should be 4, right? But this is reading 6. I didn't catch that when I was working on this earlier, but this should be 4, not 6, okay? So this is a completely different problem because they entered completely different values for x. So just pay attention to that. didn't notice that they had completely changed the value of x from 4 to 6. So based on this expression and going with x equals 6 correctly, the answer is 30. All right, so just pay attention to that. This is another example where there are errors in the book. Okay, so you can use your calculator for only part of an expression. So for example, here, where we're told to find 3x plus 6, that's the binomial in the numerator, 3x plus 6 divided by 2 plus the square root of 225 when x equals 4. And so basically, you would just find the square root of 225 using your calculator, and then you want to substitute 4 into x. So 3 times 4 is 12. 12 plus 6 is 18. 18 divided by 2 is 9, which they've done for us here. And then you would just add 9 to whatever you found as the square root of 225. And to find the square root of 225, you press the second function key and then the x squared key, because the square root key is right above the x squared key right here. So you would press second function and then the raised key to give you the square root. You enter 225 and then press enter, and you would get 15. And then all you would do is add 9, which we got from working this expression, plus the square root of 225, which is 9 plus 15, and you would get 24. Or you could just use your calculator for the whole expression. But you need to pay attention that if you want to use your calculator for the whole expression, you need to first start by entering 2 open parentheses. The first open parentheses covers this entire expression, this 3x plus 6 over 2, right? So first open your parentheses, first press open parentheses, then press open parentheses again, and then enter this expression right here, 3x plus 6, close your parentheses, and then press your division symbol, enter 2, and then close your parentheses again, so that your calculator knows that it's adding whatever you find on this side to this entire thing. You just want to make sure that your calculator is following the order of operations. And to do that, the best way to do that is to make sure that you enclose this entire thing in parentheses and then press your addition operation symbol and then the square root of 225. And you would probably maybe want to open parentheses, press the square root symbol, 225, and then close parentheses as well. It's just a safe way of making sure that your calculator is properly grouping the terms in your entire expression. That's obviously time consuming, so that's why the book is suggesting the easiest route would be just to plug in, use your calculator to just find half the expression first by finding the square root of 225, then plug in 4 into this expression, which is going to be a lot easier. You know that 3 times 4 is 12, plus 6 is 18, and 18 divided by 2 is 9. And then you can just add the 2 numbers, which is a lot easier than going through the motions and adding all the parentheses that you need to. You can save time by just using the shortcut that the book is suggesting here. Try the practice exercises. Again, same story, different day. Make sure that you're working on the practice exercises. Lesson 8 really just is about understanding polynomials, and then we'll get to actually working on polynomial expressions in lesson 9. So a polynomial is an expression with more than one term. Any combination of coefficients, variables, exponents, and constants. Specific types of polynomials include monomials. Mono means one and nomial means term. So monomials are one-term expressions like x or 2x. Binomials contain 2 terms, so 2x plus 3y, for example. That would be an example of a binomial expression. And then trinomials, tri means 3, so they contain 3 terms. The GED mathematical reasoning test will expect you to use or to understand polynomials. A polynomial is made up of terms, and since the prefix poly means many, a polynomial is a term in which many parts are being combined. So within polynomial expressions, you have more than one term. Each term in a polynomial may be made up of a combination of coefficients, variables, exponents, and constants. A coefficient includes a number such as 4, -5, or even 1/2, and it'll always come before the variable. So you'll always see like 4x or 4x plus y. With y, understand that the coefficient is 1. Coefficients can either be negative, like -25, or obviously they can be positive. If there is no coefficient next to a variable, assume that the coefficient is 1. So in the expression x plus y plus z, we assume that the coefficient in front of each variable is 1. So you could rewrite this as 1x plus 1y plus 1z, but nobody does that. It's just written x plus y plus z with the understanding that the coefficient in front of each variable is 1. Variables are letters such as x and y in polynomial terms. In the polynomial 45a squared b, the variables are a and b. So exponents or powers are a way of showing repeated multiplication, and this is also known as raising a number or a variable to a power. Polynomials must be raised to a whole number exponent. So in a polynomial expression, if you saw something like x raised to the power of 1/2, then that expression is not a polynomial because 1/2 is not a whole number. Okay, and that's just what this is trying to say. There are no negative or fractional powers in polynomials. So if you saw an expression that read 2xy raised to the power of -3, you know that that's not a polynomial because it has a negative power. In the polynomial 6x cubed, y to the 4th power, the exponents are 3 and 4. The degree of a polynomial with only one variable is the largest exponent of that variable. So for example, in the expression 4x cubed plus 3x squared minus 5, the degree is 3 because 3 is the largest exponent of x. Okay. And just reiterating, if there's no coefficient next to a variable, just assume that the coefficient is 1. Okay, as seen many times in previous lectures, and we just discussed earlier today as well. A constant is a number on its own that will always remain the same. So it's not next to a variable, it's just a number that appears on its own. So a constant can either be positive or negative depending on whether it is being added or subtracted. So in this expression, 4x cubed plus 3x squared minus 5, the constant is 5. Okay, and that just means that no matter what value you substitute for x, 5 will always be 5. So essentially, the name is self-explanatory. These two terms will vary depending on what value of x you decide to plug in there, but 5 will always be constant. Polynomials are built out of all the components above, and there are different types of polynomials, including monomials, binomials, and trinomials, and these are important to know. A monomial is a polynomial with only one term, and an example of a monomial is 4xy squared. And there was some error here, I don't remember what it was, but I changed that. So when you're studying, compare what's in the book with what's on the slides. This term is made up of a coefficient 4, two variables x and y, and then an exponent raised to the power of 2. A binomial is a polynomial with two terms. An example of a binomial is 3x plus 2. The first term is made up of a coefficient and a variable, so 3x is our first term. And then the second term consists of a constant, in this case, positive 2. A trinomial is a polynomial with 3 terms. An example of a trinomial is 4x plus y squared minus 4. The first term is made up of a coefficient and a variable. So the coefficient in this case is 4. The variable is x. The second term is made up of a coefficient, a variable, and an exponent. The coefficient being 3, the variable y, and then our exponent is the power of 2. And then the third term is made up of a constant, and this time it's a negative, or the number -4 is our constant. A few types of numbers are not categorized as polynomials and cannot be present in polynomial terms, and these include the following that are listed here. So division by a variable. So if you see a term written like this, 3 over x plus 3, or 1 over x, you know that whatever expression you're looking at is not a polynomial. If there are negative exponents, as I mentioned earlier, the exponent here was positive, that's why I changed this. But if you see a negative or a term with a negative exponent within an expression, know that the expression that you're looking at is not a polynomial. That's when I say expression, obviously, I just mean a group of terms written together with different operation symbols in between them, right? If you see a fractional exponent, so in this example, 3a raised to the power of 1/2, you know that that term is not a polynomial. And then if you see a variable inside of a radical, so the square root symbol is also called a radical sometimes. If you see a variable inside of a radical, know that the expression that you're looking at is not a polynomial. But if you see a whole number inside of a radical, then that term or that expression that you're looking at, as long as none of these other exceptions apply, then the term is a true polynomial, because the square root of 225, for example, that we saw earlier, will give you a whole number, 15, right? So the square root of 225 is a number, and that's always going to be constant. So in other words, if you were looking at x plus 225, okay, that's a binomial, right? You're looking at x plus 225. If you decide that x was 10, the square root of 225 will always be 15. If you decided that x was 1,000, the square root of 225 would still be 15, meaning that the square root of 225 is constant, right? So in that particular binomial, let's say you had x plus the square root of 225 plus x plus the square root of 225. That counts as a polynomial. So in that example, the square root of 225 counts as a constant, and so that expression counts as a polynomial, okay? And I just wanted to point that out because the difference would be that in this particular instance, we don't know what x is. So if one day x is 10 and then tomorrow x is 20, well, the square root of 10 and the square root of 20 are two different numbers. And so that's why when you see a variable under a radical or under a square root sign, that expression doesn't count as a polynomial because we don't know what that value is. It changes all the time, right? In a polynomial term, however, you can divide by a constant or have numbers inside a radical, as I just spent a lot of energy explaining, okay? For example, if you had 4x over 12, that's allowed. Why? Because whatever x is will always be by 4 over 12. For example, if x is 1 and you multiplied 1 by 4 over 12, the value of 1 or the number 1 is being multiplied by a value that's essentially constant, being 4 over 12, right? So for example, if x is 2, you would still have to multiply x by what? 4 over 12. If x is 90, you would still have to multiply it by what? 4 over 12, okay? So if you like, you can think of 4 over 12 as a regulator, right? Whatever value x takes on, 4 over 12 is going to regulate that value. And then, I've already spent time explaining why the square root of 10 counts as a constant, right? Because whatever value you find the square root of 10 to be will always be constant in the context of the polynomial expression that you have. So more practice exercises starting on page 890 to 892. All right, and then the rest of today's lesson is going to be on simplifying polynomials. So the key ideas that you want to pay attention to is that like terms can be combined and unlike terms cannot be combined. Like terms are either numbers, positive or negative, or variables with the same degree of exponents. Polynomials with unlike terms cannot be simplified. And this will make more sense as we work on examples. When you're working with polynomials, you want to work to combine like terms. Like terms have variables that are the same or are terms that have the same variable raised to the same power or exponent. So for example, 8x cubed and 4x cubed are like terms because they both have the same variable x, and x is raised to the same exponent 3. 5y and 3y are also like terms because they both have y in their terms. Unlike terms have variables that are different or have the same variable raised to different powers. So for example, 3a and 5b are unlike terms, and the terms 9x and 7x squared are unlike terms because the variables are raised to different powers. So as we saw last time, when you see x written without a power, the assumption is that x is raised to the power of 1. You can only combine like terms when simplifying polynomials. Unlike terms cannot be combined. So for example, in this polynomial, 7x squared plus 4x cubed, you cannot add these two terms together because the powers on both terms are different. However, with this example, 7x squared plus 4x squared, you can combine the terms that all have the same variables and the same exponent. So 7x squared plus 4x squared turns out to be 11x squared. This was another portion of the chapter that had errors, so just pay attention to that when you're studying so you don't get confused. This example is asking to combine like terms in the polynomial 4y cubed plus 2x cubed minus 7x cubed. So the first thing that you want to do is you want to identify your like terms and then group them together. So in this particular example, 4y cubed, and well, 4y cubed is the only expression of its kind, I should say. So you would just simply write that down. And then 2x cubed and 7x cubed, we know are like terms based on the information that we just covered. They share the same power and the same variable. So then you would combine those two together. So x cubed plus 2x cubed gives you negative 5x cubed. And then you would just simply write down 4y cubed as is because there's nothing to subtract from it or add to it. No terms like it. And so your simplified polynomial term turns out to be 4y cubed minus 5x cubed. And if you notice, we're just treating this as if it were a whole number, right? So since x cubed, 7x cubed, and 2x cubed share the same variable and the same power, just look at the value that's written right next to them. In this case, negative 7 and 2, and then just combine them as you would do with your regular addition or subtraction. We know that negative 7 plus 2 is negative 5. And so that's why we have negative 5x cubed. All right, so when you're working with polynomials, treat the minus sign before a coefficient or a constant as an indicator of a negative number. This will help you combine like terms using rules of signed numbers that you learned on pages 316 to 318. So for example, with this expression, we treated this negative sign in front of 7 as being applicable to the whole term, meaning that we're considering this whole term negative because there's a negative sign in front of it. And so you would then just carry on with your procedure based on that knowledge. So again, we decided that negative 7x cubed plus 5x cubed, plus 2x cubed is negative 5x cubed. Okay. Some polynomials may contain both like and unlike terms, and the example that follows will show how like and unlike terms are handled when you have to simplify a polynomial. Start by combining the like terms with the largest exponents, and then proceed to the terms with the smaller exponents, okay? And so here, let me zoom in. This is easier to see. I highlighted in different colors like terms so that this is easier to follow. Okay, so we're being asked to simplify the polynomial 7x raised to the power of 4 minus 13x squared plus x raised to the power of 4 plus 2x squared plus 5x plus 3 plus x. You want to start by combining the like terms with the largest degree, which is 4. You can see that here we have one term that's raised to the power of 4, and we have our other term raised to the power of 4. So we're going to combine those two terms. 7x raised to the power of 4 plus x raised to the power of 4 is 8x to the power of 4. And again, you know that since the variables and their corresponding powers are similar, you can just ignore those and then treat this as you would a regular addition. We already know that we assume that there's a 1 in front of the variable when there's nothing written next to it. So 7 plus 1 is 8. Then you have, you go on to group your next set of terms, right? So now we have 8x squared. You write that down, and then look at your expression for the next terms that are similar. We have here negative 13x squared, and we have 2x squared, right? So you would group those together. Negative 13 plus 2 is negative 11. From negative 13x squared plus 2x squared, we get negative 11 squared. Then you would continue the same thing until you've exhausted all the terms in your expression, right? So next we are looking for terms with only 1 or with no power. So 5x plus x would be the next set of terms that we would group. 5x plus x is 6x. And again, we're just ignoring the variables and their associated powers, in this case 1, or you can consider it as having no power. We already know that when we don't see a coefficient or a number in front of a variable, we assume that that number or coefficient is 1. So 5 plus 1 is 6. That means that 5x plus x is 6x. Then you write down 3 because it's the only term in this expression that's a constant. And so now you have 8x raised to the power of 4, which we got from combining our first set of like terms, minus 11x squared, which we got from combining our second set of like terms, plus 6x, which we got from combining our third set of like terms, plus 3, which is our constant, okay? If this particular expression had 3 plus 5, obviously you would combine those and you would here write 8, 3 plus 5 is 8, right? If it had 3 plus 5 plus 2, you would add those together, you'd get 10, you would write 10 here, okay? In this particular instance, we only have one constant, and so you reflect that in your answer. This is what this note is trying to tell you here, that sometimes polynomials may contain both like and unlike terms, and you simply want to make sure that you're grouping the like terms and leaving the unlike terms, if they happen to be a constant on their own, for example, as they are, and expressing the entire thing in simplified form, reflecting the like and unlike terms, but you can't add like and unlike terms together, right? So in this particular instance, you can't do anything else with this expression because it's full of unlike terms, right? Yeah, and so essentially that's what this note is telling you here, that this is as much as you can simplify the polynomial by combining the like terms as we've already done. The simplified polynomial must remain as it is, okay? And then if, for instance, you're given a value of x, let's say x is 1, you would just go back into your simplified expression, you would plug in 1 everywhere where you saw x. So you would rewrite this as 8 times 1 raised to the power of 4 minus 11 times 1 raised to the power of 2 plus 6 times 1 plus 3. Okay, and then you would report whatever answer you found. All right. Practice questions or practice exercises, I should say, starting on page 895 to 897. And that's essentially it for today's lecture. Very short and sweet, I think. Do you have any questions?
No, I'm okay. I'm all right.
Okay, all right. So that's it for today. I will see you next week. Enjoy your weekend.
All right. No, you too.
Okay.
Bye.